Hello everybody, my name is Neeraja Rentachintala. I am in product management team at Mapr. Today I will be briefly talking about how Apache drill achieves low latency performance on large scale datasets. For those of you who are not familiar with it, Apache drill is an open source interactive SQL on Hadoop query engine with which you can do data exploration as well as BI and ad hoc queries directly on top of big data using familiar ANSI SQL tools such as Tableau and MicroStrategy. In the next few minutes, I will be talking about some of the core architectural elements as well as features which enable drill to provide this interactive performance experience. At the heart of it, drill is a distributed SQL query engine. The core daemon in drill is called DrillBit. This is a service that you would install on all the data nodes in the Hadoop cluster. It's not a requirement to install drill on all the data nodes. You can do certainly a partial set of nodes, but installing on all the nodes gives drill ability to achieve data locality at the query execution time. Data locality is the ability to push down the processing to the node where the data lives rather than trying to bring the data over the network at the query execution time. So let's take a look at the query execution flow. The SQL query comes in from a client. This could be a JDBC client, ODBC, CLI, REST endpoint. The query comes in and the query is accepted by a drill bit. The drill bit that accepts the request acts as a foreman or a coordinator for that specific request. As a client application, you could directly submit to a drill bit, or you could talk to a zookeeper quorum, which in turn would route the request to a specific drill bit. Once a drill bit receives the request, it parses the query, and then it determines what is the best way to execute this particular query. What is the most optimal way to execute the query? So a drill allows to do a variety of rule-based as well as cost-based optimizations in addition to being aware of the data locality while during the query planning. Once the best query plan is determined, drill splits the query plan into a number of pieces called fragments, query plan fragments. So the drill bit, the coordinator drill bit, talks to the zookeeper, determines what are all the other drill bits that are available in the cluster. Then it gets the location of the data. Combining that information, it determines what are all the drill bits that can handle this particular list of query plan fragments. Then it distributes the work to the other drill bits in the cluster. Each drill bit does its own processing of the query plan fragment. They return the results back to the original drill bit, and the drill bit returns the results to the client. So during the execution, each of the drill bits would be interacting with the underlying storage systems. So this could be files, as I have written here. This is DFS, which represents a distributed file system. It could be a HBase, it could be Hive, it could be MongoDB, it could be MapRDB, it could be any other storage system drill is configured to work with. And the important thing to realize here is that each of these drill bits are same. So this is a completely scale out MPP architecture. So the request from client can go to any drill bit. That is how drill scales. There is no master slave architecture. So today I could deploy drill on one node if that is sufficient for my needs. I can grow it to 10 nodes tomorrow. I can grow it to 100 nodes, 1000 nodes, depending on the amount of data that you want to process, depending on the number of users you want to support, depending on the performance that you want to achieve, the SLA goals that you want to meet. You can scale the drill cluster, you can shrink the drill cluster without hitting any bottlenecks, either on the networking side or on the processing side. So this is a completely scale out MPP query engine. So this is the foundational element during the drill execution which allows drill to provide performance. In addition to the core distributed execution, there are a variety of other execution architectural elements which allow drill to provide this performance. I will briefly describe each of these characteristics in detail. So the first aspect here is columnar execution. So drill is columnar in storage as well as in memory. So what does that mean? What does it mean by drill in columnar in storage is drill is optimized for columnar formats such as Parquet. So if I'm querying Parquet data files with drill, it saves on disk I/O by reading only the specific columns that are required to satisfy the query. It's not just that. Once the data is read into the memory, drill continues to keep the data in a columnar format. So the internal data model for drill is an in-memory columnar hierarchical data model. So the benefit is, with the columnar execution, the drill doesn't need to materialize the data into a row format. So it is doing joins, aggregation, sorting, all the SQL operations directly on the columnar data without having to change the structure. So this not only just gives performance, it also saves the memory footprint that drill has to occupy at the query execution time. So columnar execution is a very foundational element in achieving performance. The next aspect, which goes very much hand in hand with the columnar execution, is vectorized processing. So this is a very recently, I wouldn't say recently, this is actually a pretty common technique in database systems, in the traditional MPP database systems, but this is fairly new in the context of Hadoop. So the idea of vectorized processing is, rather than operating on a single value from a single record at a given time, drill allows the CPU to operate on what is called vectors. So these are also called record batches. So the vector is basically an array of values from a set of records in a table. So think about doing a null check on a billion records. So the vectorized processing, the technical premise for it is to make sure that you can really take advantage of the modern CPU designs and deeply pipeline CPU architectures. So keeping these CPU pipelines busy to achieve the performance as well as the CPU efficiencies is not something that you would traditionally get with traditional RDBMS kind of systems, just because of the code complexity, which is where the performance benefits of drill comes into a lot more shine. One aspect around the columnar execution is, some of you might have heard about a recently announced project called Apache Arrow. So the in-memory data model for drill, as I was mentioning, is a columnar hierarchical data model. Now this is actually spun out as a separate project and contributed to the community as a new open source project called Apache Arrow. And the goal of that project is to really standardize the data representation across a variety of storage systems as well as processing frameworks, such as Kudu, Impala, Spark, etc. So this is kind of the standard for the big data analytics. Moving on, the next aspect here is optimistic in-memory execution. First of all, one thing to realize is drill does not use MapReduce, drill does not use Spark. This is an engine that is built ground up for performance on complex as well as hierarchical data sets. So what does it mean by optimistic? This means that drill assumes that the chance of getting a failure, such as hardware failures, node failures, is uncommon during the short execution of a query. So it tries to do as much as execution as possible in memory without writing anything to disk for checkpointing and recovery purposes. The idea is that the model that is used from a technical terms is called pipeline execution. So rather than scheduling one task at a time, drill in a pipeline fashion schedules all the tasks at once. And these tasks are getting executed, data is getting moved between the various pipelines, trying to do everything in memory, and writing to disk only if there isn't sufficient memory. So this again is a very, very core aspect of achieving seconds performance rather than minutes kind of performance that you would see with traditional batch-based paradigms. So columnar execution, vectorized processing, optimistic in-memory execution, they complement the distributed query execution capabilities. There are a lot more. One example is runtime code compilation. Again, runtime code generation is very efficient compared to the interpreted kind of query execution. So drill allows you to actually generate very, very highly efficient custom code for every query, for every operator dynamically. So this again is a very efficient way to execute the query. So a combination of, there are a lot more that you can certainly read into the documentation and learn more about it. But I would say the distributed execution and the combination of columnar vectorized processing, in-memory execution, they form the foundation for drill execution around performance. There is a lot that drill does around optimization in order to achieve performance. So we'll cover that in a separate video. Please check out mapper.com. Thank you for watching.